Professor HAG, and head of the Department of Computer Science and Engineering at the Indian Institute of Technology, Roorkee. He also serves as a joint faculty member at the Mehta Family School of Data Science and Artificial Intelligence, IIT Roorkee. He received his PhD in computer science and engineering from IIT Madras and has since established a distinguished academic and research career. He currently leads the Machine Vision and Intelligence Laboratory at IIT Roorkee, where he directs cutting edge research in a wide array of domains, including image and video processing, medical imaging, activity recognition, pattern analysis, privacy preserving computing, and biometric security systems. Professor Bala Subramaniam has authored over 250 peer reviewed publications in high impact international journals and conferences, reflecting his sustained research excellence and the scholarly influence. His interdisciplinary work bridges foundational research with real world applications, advancing the frontiers of artificial intelligence and intelligent systems. We are honored to have you, sir, with us and eagerly anticipate the deep insights and the perspectives that you'll share during your session. Welcome, sir. Over to you.
Yeah. One second, I'm sharing.
Yes, sir.
Is it visible?
Yes, sir. Yes, sir. Your screen is visible to us.
Okay. So, very good morning, everyone. And I thank Dr. Priyanka for the brief introduction and give me the opportunity. Right. In fact, I am taking two sessions, and this will be my first session. So, in the first session, we are going to see principal component analysis and linear discriminant analysis. Hope my voice is audible.
Yes, sir. Your voice is
Okay.
audible.
Thank you. So the next 1 hour 15 minutes we'll talk about the principal component analysis and LDA. So I have the applications for LDA, and for the case of PCA anyway, I am going to give one more session. So in that, all right, I will cover the applications for PCA. So the agenda of today's talk is the curse of dimensionality. Right? What do you mean by curse of dimensionality? What do you mean by dimensionality reduction? And then I'll slowly start with PCA concepts and the mechanics of PCA and how PCA can be useful for the dimensionality reduction. What is the difference between loading and eigenvectors, right, in PCA? Then we'll talk about the applications of PCA and advantages and disadvantages of PCA. So then I'll quickly go into the linear discriminant analysis. So under linear discriminant analysis, we are going to talk about within class matrix and between class matrix, right? So this is the brief agenda, and I'll start with the curse of dimensionality. So what do you mean by curse of dimensionality? All right. So suppose you are having a high number of features, or the physical example, if you overcook the curry, right? So which is not good. So at the same time, suppose you have, right? Let us assume you have a high number of features. So having a high number of features is good, but the problem is, right, when you are predicting certain models, it won't be good, right? So how to reduce the number of features? Correct. So what are all the features are so important? So let us consider those features. All right. So suppose if you have the number of features which are too high when you are comparing with the number of samples, right? So then the predictive power will get lost, and also the large number of features suppose you have, so you will have the lot of noise, right, in the data. So that is also resulting the overfitting of the model. So this is called the curse of dimensionality. So to reduce this curse of dimensionality, right, I don't want to use all the features. Suppose I have n features, you may ask the question, so can we use only 5 features out of this n, right? 5 out of n problem. So we can remove all other n minus 5 features. All right. So how do you reduce these features, right? How do you reduce? For example, n features are considered as n dimensions. So can we go for, let us say, right, 5 dimensions? N2, assume that n is a very big number and you are going to up to 5 features. So this is called the curse of dimensionality. So now, how do you do the dimensionality reduction? Right. So for this, we are going to talk about PCA and LDA. All right. So I hope mostly all are from mathematics background. So we require the concepts of eigenvalues and eigenvectors. All right. So that means I am going to eliminate certain features. So how I am going to eliminate certain features? So we are going to find out, let us say, the eigenvalues and the corresponding eigenvectors. So which matrix you are going to find out the eigenvalues, right? So we are going to call it as a covariance matrix. So that means when you apply the covariance filters, and the low variance filters will be drop out. All right. So that means I'm going to consider the high variance. So these high variance are mostly important or applicable for further problem, or if you want to talk about the prediction. So the high variance component are going to helpful, right? So how we are going to do that? All right. So for this we have principal component analysis, PCA. All right. So now, what is the difference between feature selection and feature extraction or feature elimination? All right. So suppose I have, let us say, n features. For example, the satellite data. All right. The satellite images. We have assumed that you have n data. All these n, all right, n bands. They call it as n bands. Satellite image data, hyperspectral or multispectral imaging. They call bands, right? XY, which is nothing but the image, and z axis you have number of bands, right? So these number of bands all may not be useful, right? I want to reduce, I want to get rid of the same concept, right? The dimensionality reduction I told. So in the third dimension, I don't want this number of features. So what I will do, I will try to reduce, or I want to select only the important bands. All right. So the bands that which are not useful, you call it as the elimination. You are eliminating the features. And similarly, other important concept is the feature extraction. All right. I may use all the bands. All right. Let us assume the band numbers are, let us say, Z1, Z2, Z3, etc. up to Zn. But from this vector, n-dimensional vector, I am going to have m-dimensional vector where m is strictly less than n. Right? I will have, let us assume, some z1 dash, z2 dash, etc., etc., zm dash. Right? M is strictly less than n. N is the original data. So now this z1 dash, z2 dash, etc., zm dash, so they will be having all the information about the original data. Whereas in the previous case, you have simply eliminated. Right? You have z1, z2, z3, zn. Only you are taking a subset. And here in this case, you have z1 dash, z2 dash, etc., zm dash, which contain the property, the original property of z1, z2, z3, etc., zn. So this is the major difference between feature selection and feature extraction, or you call it as a feature elimination. All right. So feature elimination, or you call it as a feature selection, whichever you are selecting, and feature extraction. So this is a major difference. So in terms of vectors, So one is the subset. All right. So whichever your elimination subset, whichever is eliminated, you call future elimination, or whichever you are selected in the subset, you call future selection. But in the case of extraction, it has the original property of all the vectors, right? Future vectors. You call it as future extraction. So now, principal component analysis, it's a unsupervised machine learning algorithm. All right? It's unsupervised machine learning algorithm. I hope everybody knows the difference between supervised learning and unsupervised learning. Supervised learning, so your label will be there. For example, you have a set of fruits and you have a robo. And you are training the robo where you are telling this is apple, this is banana, this is grapes, etc. That means you are giving a label. Right? You are assigning a label. Based on the label, you are training the robo. Right? And then during testing, you are seeing whether the robo is predicting properly or not. So that is called supervised learning algorithm. Whereas unsupervised learning, I am not having any label. I have only fruits and a robo. So with the help of, let us say, color, shape, texture, all or nothing but the features. So based on these features, can robo predict itself? You call that problem is an unsupervised learning problem. So principal component analysis goes under unsupervised learning. Also, it is a non-parametric. That means it need not follow any distributions. Right? So you have a normal distribution, you have uniform distribution, chi-square distribution, no need to follow. Right? So here it is a non-parametric statistical technique. All right. So the main idea is you have to preserve the largest variance. Right? For example, we are going to talk about eigenvalue and eigenvectors. So that eigenvector will hold the largest variance. So that is what the main idea. All right. Also, all right, this principal component analysis that creates a new synthetic features to represent original features. Yes, suppose I have selected, let us say, only the top three vectors, top three eigenvalues corresponding eigenvectors. Right. So these eigenvectors will serve the purpose and it will preserve the largest variance. All right. So let us say I have three vectors v1, v2, v3. All right. Out of all the n-dimensional vectors, n-dimensional feature vectors. All right. So this v1, v2, v3, I'm selecting only these three. I'm extracting only these three, and these three will hold, the complete. All right. So the complete information. Or these three are enough for my further prediction, right? So that is what the idea of the preserving the largest variance. So it is nothing but the principal component analysis. Yes, once I have the eigenvectors, it's a linear combination of the features, right? So that will determine the magnitude and direction of the maximum variance. All right. So we know that when we have, let us assume we have three vectors, three eigenvectors, right? They are orthonormal to each other. Correct. And also, I hope mostly all are having a mathematics background, so I don't need to go much into the eigenvalue eigenvectors. Right. So once you know the eigenvectors, assume that I have three eigenvectors, they are orthogonal to each other. Right. So these three eigenvectors, assume 3 out of n. Right. So that will determine the magnitude and direction of the maximum variance, and they are not correlated to each other. Right. So that is the property of the eigenvectors, and the number of principal components is equal to the number of original features. So now, how do you do this principal component analysis? Right. So let us go by algorithm, and then we will talk about the mathematics behind. All right. So you will have to standardize the data. Given data will be standardized. Let us say m cross n matrix. All right. M cross n data. All right. So number of columns and number of rows. Correct. So let us assume m cross n. M is the number of rows in given data. All right. So then we have to standardize the data, and then let us see how we are going to generate the covariance matrix. So once you have the covariance matrix, find out the eigenvalue eigenvectors. You call it as eigen decomposition, and then right, assume that I am writing the eigenvalues in the descending order. So let us assume I choose the top eigenvalues. So the top eigenvalues corresponding eigenvectors we have to take it. Right. So this is the main idea. So once you are taking the corresponding eigenvectors of the top eigenvalues, so that will determine, all right. In fact, those eigenvectors will have the maximum variance. That means the maximum information about the model. All right. Suppose I am doing, let us say, face recognition or fingerprint matching. Right. So I have chosen, let us say, top three eigenvectors, right? Top three eigenvalues and the corresponding eigenvectors. So these eigenvectors will have the maximum information, right? That is the physical meaning, and statistically they will have the maximum variance. So now, before going into the problem, one should know what do you mean by signal to noise ratio, right? SNR. So signal. So given right, given time, what is a signal? We know that. Suppose I am talking, or if you're listening a song, you will get the pattern, right? One dimensional pattern, which is a signal, right? So x-axis, and then you will have a corresponding y-axis, or let us say t, right? You will have a signal. So here you can see, all right? So I have x mean x max and y mean y max. I have some signal, which is a two-dimensional signal, all right? The plus sign. So now assume that I am fitting this by a straight line, right? These data by a straight line, right? So some of the points will lie on that straight line and some of them are away, right? So those who are away, so let us assume they will have some spread, right? So due to the random factor, so you call that as a noise, all right? So assume that I have a, let us say, a straight line, and most or some of the points, right, so will lie on a straight line. So that means there is no noise. So rest of them will be around that straight line, right? Rest of the points will be around. You call it as a spread, so you call it as a noise. Now I take the variance of signal, I define a signal, right? So those plus points are nothing but a signal. I take the variance of the signal, and then I divide this by the variance of noise. Right, so it's a famous question. Those who are working in signal processing, what do you mean by SNR? And those who are working in image processing, you should know PSNR, peak signal to noise ratio. Right? So statistically, which is nothing but variance of signal divided by variance of noise. All right. So greater SNR, your model will be better. So I have to get more SNR. So that means, right? For example, your let us say you are taking a ECG signal, heart, or EEG signal for brain. All right. So around the spectrum, if I don't have right more number of points, right? For example, if I get exactly that curve, single curve, that means it is not having noise. All right, your signal does not have a noise. So assume that if you have a noise, you can see, right, your the curve will look like, right, the zigzag, right? So too many noise. All right. So how do I find statistically? I can find variance of signal divided by variance of noise. So you call it a signal to noise ratio. In some of the cases, you have to manually add the noise. For example, many image processing algorithms, let us say you are working on a watermarking algorithm, right? You have to check your robustness of your algorithm. You are adding a noise, right? You have an original image also. Original image is nothing but a signal. Then you find what is your variance of signal, what is your variance of noise, and then variance of signal divided by variance of noise, you call it as signal to noise ratio, right? And PSNR, peak signal to noise ratio, right? Okay, so let us go back to your principal component, covariance matrix. So how do you find the covariance matrix? So let us say you have a one-dimensional data, right? Only one-dimensional data, set of points. right? So assume that you are given a one-dimensional points, you are finding out the average. Average is x bar. So how do you define a variance? Summation of xi minus x bar the whole square divided by n. That is the variance. What do you mean by covariance? Assume that I have two data. Let us say the 2D point, right? X comma y, right? You have along x the values in the column, along y you have values in, right, in the column. Xy, set of xy points. So now I have to find the covariance of x comma y, right? So which is defined as summation of xi minus x bar multiplied by yi minus y bar divided by n, right? So now, so let us consider the covariance matrix for, you are given the three-dimensional points x, y, z, right? X column, y column, and z column. So how do you find a covariance matrix? So you can see over here. See, covariance of x comma x is nothing but the variance, right? When you substitute this, the second formula, it is nothing but xi minus x bar the whole square divided by n, which is nothing but a variance. So the column is variance of x, variance of y, and variance of z. And it is symmetric, right? Covariance of x comma y is same as covariance of y comma x, right? You just substitute, which is true, correct? So we can find the covariance matrix of the three-dimensional points, right? So you can extend this. You have a four column or a five column, you can find the covariance matrix, right? So x1 x2 x1 x3 x1 x4 x1 x5, right? Whatever be the combination, right? So naturally you will get a square matrix, whatever be the dimension, right? You check. So for example, you have x1 x2 x3 x4 and x5, you will have, right, covariance of x1, right, x2 x2 x3 x3 x4 x4 x5 x5. So this will be your main diagram. Rest you can fill it out, right? X2 x3, which is same as covariance of x3 x2, right? So any dimension if you give, you will get, for example, the three-dimensional case you are getting 3 by 3, n-dimensional case you will get n by n. Okay, so now the covariance matrix is, what do you call, square matrix. So once you are given a square matrix, right, since most of you are from mathematics background, you can find the eigenvalues, right? This square matrix, this covariance matrix, you can find the eigenvalues, right? So you have lot of properties for eigenvalues, right? So given Ax, how do you define eigenvalue? So given a matrix A, and if you define lambda is the eigenvalue, and the corresponding x vector is the eigenvector, then we know that Ax is equal to lambda x. All right, or determinant of a minus lambda I equal to 0, you can find always the value lambda, right? So when it is satisfying the equation Ax is equal to lambda x, right, the characteristic equation, we can say that, right, lambda is the eigenvalue of a, and then since you are given Ax is equal to lambda x, a minus lambda into x, right, which is equal to 0, and the vector that is satisfying this characteristic equation, you call x as the eigenvector, right? So how do you calculate the eigenvalues and eigenvectors? So given covariance matrix, it is a square matrix. So from this square matrix, I can always find out the eigenvalues and eigenvectors. Let us say you're 3 by 3, you will get 3 eigenvalues. Assume that you have n by n, right? In fact, n dimensional points, you will have n cross n matrix. So that means you will have lambda 1, lambda 2, etc. lambda n, and the corresponding eigenvectors, let us say x1, x2, x3, xn. Right. So how now I will use this for the dimensionality reduction. Right. So assume that I have the principal components. Let us say n. So here without loss of generality, let us say 5 components, 0, 1, 2, 3, 4. right? So now you can see that I have drawn this, right? All the eigenvectors, I put it as a explained variance ratio, right? I put it as a explained variance ratio, right? So what we have to do, we have to find out the largest eigenvalues, right? The largest eigenvalues corresponding eigenvectors. Let us assume lambda 1 greater than lambda 2 greater than lambda 3 greater than lambda 4 greater than lambda 5, right? So now you will have the vectors, I corresponding eigenvectors. So the corresponding eigenvectors, if I put the magnitude, all right, we use the magnitude, you call it as explained variance ratio. So I can plot like this. So you can see the first, right, you can see here, right, the largest eigenvalues corresponding magnitude. You call it as explained variance ratio. And the next one, second eigenvalue, third, right? So now, so let us assume cumulatively I am, right? For example, I'm adding this, my graph will go like this. I'm adding this. So what I can do, I can choose some cutoff. For example, I'm choosing a cutoff here. I want to go up to 99.99. So that means I will choose only the top three. So top three is enough. I can contain 99.99% of, let us say, the variance. Okay, fine. Rest of them are very small contribution. Even I will, even if I can eliminate, not a problem, right? Your prediction model, right, still works. So that means I have a 5 by 5 matrix, correct? And I reduced fourth and fifth, right, dimension. Now I use only first, second, third, right? Or here it is 0, 1, 2, right? I use 0, 1, 2, eliminate 3 and 4, right? I don't want to use. So I select, I extract only 0, 1, 2. All right. I can have 99.99% of what you call variance. All right. So now what I am doing physically, I am not able to solve the problem in 5 dimension. All right. I am not able to solve the problem in 5 dimension, but I am reducing to 3 dimension. So now 3 dimension I can able to solve, right? The similar theory will work for LDA. Once I explain LDA, so you can able to see that, right? So that is what the physical idea. I am not able to solve the problem in 5 dimension. I'll reduce to 3 dimension. That is called the dimensionality reduction. How do you reduce? I take the top eigenvalues, right? Suppose you have 5 eigenvalues, write it in descending order. From there, I'll choose top three, all right, or top two, according to your problem. So the top three, assume that without loss of generality, top three. So I choose top three, and from these top three values, I can able to, right. So these top three values, I can able to find out the corresponding eigenvectors, and once I have the eigenvectors, so now I can solve the problem in the 3 dimension, right? So that is called the dimensionality reduction. That means the third and fourth here, 0, 1, 2, we are keeping, 3 and 4 we are reducing, right? So 3 and 4 we are eliminating. So therefore 5 will be reduced to 3. That's called the dimensionality reduction. I hope it is clear for everyone. So let us consider one example, right? So assume that here we have 4 dimensional points, right? 4 dimensional features, x1, x2, x3, and x4. So if you are given 4 dimensional features, right? So we know that we will get 4 by 4 matrix, right? Where covariance matrix will be 4 by 4. How do you write covariance matrix? That only main diagonal. So covariance of x1, x1, covariance of x2, x2, x3, x3, x4, x4. So rest you will fill it, right? So we have an idea. So now before that, what you have to do? You have to standardize the data, normalize the data, right? How do you normalize the data? X minus x bar. X bar is the mean divided by standard deviation, right? My normalized data will be like this, right? Given data is x, I am finding, let us say, x1 bar, x2 bar, x3 bar, and x4 bar. Find out this z. right? Z variate. Once I find Z variate with the help of standard deviation and mean, right? For the grading, right? The grading point of view, we find that Z variate in the usual, right? The grading concepts, marks and grading concepts. So we use this. Same thing we use. That means you call it as standardization of the data. Once you standardize the standardized data will look like this, right? So this is what you are seeing, the standardized data, right? Now you need the covariance of, right, x comma y, substitute on this, right? So we have already studied xi minus x bar is nothing but mean, y bar is nothing but mean of y, x bar is nothing but mean of x, right? Find out covariance of x comma y, right? So in fact, you find covariance of x1, covariance of x2, x3, x4, right? So in fact, you can see, all right, the main diagonal. And x2, x1, covariance of x1, x2, same as x2, x1, minus 0.69. Right? So now you found the covariance matrix, so which is the 4 by 4 matrix. So now with the help of this 4 by 4 matrix, right, I am finding out the eigenvalue and eigenvectors of this matrix. Right? So I have to get 4 eigenvalues and 4 eigenvectors. You can see, right, eigenvalues. Lambda 1 is 4.38 into 10 power 0. Another one is 5.55 into 10 power minus 1, 10 power minus 2, 10 power minus 4. Right? So these are all written in descending order. Right? So assume that you know how to find out the eigenvalues and the corresponding eigenvectors. And in fact, the last column is saying that, right, the last data is saying that eigenvectors, I have written those eigenvectors in column wise. Right? We know that they are all orthonormal to each other. Suppose I have v1, v2, v3, v4 eigenvectors. We know they are orthonormal to each other. Correct? So this is how I found the eigenvectors. Now, assume that if I choose only two eigenvectors, right, corresponding to the top eigenvalues. What is the top eigenvalue? That 4.38, and another one is 5.55 into 10 power minus 1. All right, this is a top value. So let us assume lambda 1 and lambda 2 I am selecting, lambda 3 and lambda 4 I am discarding. So when I do this, you can see I have 87.67% of variance PC1 has. Principal component 1 has this many number of variance and PC2 has 11.1. So assume that if I choose only PC1 and PC2, I discard PC3 and PC4. That means it has 98% of the variance. Right? Or if I choose PC3, 99%, 99 point something percentage, I discard PC4. PC4 will not contribute anything for this variance. Almost, right? Point not. Right? So without loss of generality, let us consider PC1 and PC2. That means the 4-dimensional problem is now reduced to 2-dimensional, and in that 2-dimensional, I can able to solve the problem. Right? So that is what the idea of the principal component analysis. Now, I discuss in terms of eigenvalues and eigenvectors. What do you mean by variable loading? So variable loading, it's almost similar. All of you have a mathematics background. So I define eigenvector into the square root of eigenvalue. V1 into square root of lambda 1. Right? Or in general, Vi into square root of lambda I. So when I do this, right, the eigenvector, when I multiply with the magnitude of the square root of eigenvalue, right, I call it as a loading. Right? I call it as a loading. So then I will have, obviously, right, I will have PC1 and PC2. Assume that we consider PC1 and PC2, and then I am going to compute loading. So loading in the sense I am going to multiply the eigenvector by the square root of eigenvalue. right? So you will get this, right? So this will give you some idea, right? So X1 is having, for example, X1, strong positive relation with PC1 and strong negative relation with PC2, principal component 1, right? So towards PC1, 0.98, strong positive relation with PC1, strong negative relation with PC1. X2, strong negative relation with both PC1 and PC2. X3, right? The strong positive relation with PC1. X4 is also, right? And then when I talked about X3, it's a very, minimum or very less negative relation, right? With PC2. X4 is also, right? Very minimum positive relation with PC2. So this idea you will get when you multiply your eigenvectors with the square root of eigenvalues. You call it as loading, right? So now I have certain difference between loading and eigenvectors. Eigenvectors, you know, all of you know, and loading you might have used it in the notation, right? The Vi is a vector, eigenvector multiplied by square root of lambda I. Vi multiplied with square root of lambda I. You call it as loadings, right? So load is nothing but the variance magnitude. So this will give you the magnitude, right, and the variance. That is what the main idea of loading. And in the case of eigenvector, it is just a coefficient of orthogonal transformation of projection. Right. So when we multiply eigenvector with the square root of eigenvalue, you call it as a loading. And here you will have eigenvalue. So those eigenvalues are nothing but the variance of the principal components. Right. So in fact, when you do lambda I into square root of lambda I into Vi, so which is nothing but, right, geometrically speaking, which is nothing but the rotation, right, which is nothing but the kind of rotation. Here in this case, rotating the principal components coefficient is very rarely done in the case of eigenvector. So it is nothing but a vector. In the case of, right, eigenvector, you have, let us say, v1, v2, v3. Here when I do with, right, certain values, right, I have eigenvalue, square root of eigenvalue, and then with the vector. Right, so we call this as a loading. So there's a major difference between the loadings and eigenvectors, right? So the main applications of PCA is dimensionality reduction. We know that, right? Once you find out the eigenvalue, corresponding eigenvector, assume that I choose the top eigenvalues, corresponding eigenvectors, top eigenvalues. Let us say 2 out of 4 or 2 out of 5. All right. So I reduce 3, 4, 5. You call it as a dimensionality reduction. And it improves signal to noise ratio. And in fact, so this will be useful for future extraction, right? So assume that the top eigenvalues corresponding eigenvectors, let us say v1, v2. The v1, v2 are the extracted features, right? For the future extraction, this algorithm is useful. And moreover, as I already started this with unsupervised learning, all right? So extracting a feature, for example, the same, go back to the robo and fruits problem. It is extracting the features. I have v1, v2, v3, color, texture, and shape, right? So based on that, these features I can able to classify, all right? And you have several applications in terms of image processing, right? For example, face recognition, fingerprint matching, right? Any pattern recognition problem, we use the principal component analysis, right? So the main advantage is reducing the dimensions, and the correlated features will be removed, and the performance of an algorithm will be improved because you have reduced the features and you are working for the selected features, right? And it is a low noise sensitivity. Whereas we are assuming that the feature sets are correlated, right? So you may ask the question, why you are going for the covariance of x1, x2, x2, x3, right? How do you ensure that they are correlated to each other, right? So this algorithm, they are assuming it, right? And it is very sensitive to outliers. Yes, for example, we have taken that signal to noise ratio, but assume that two anomalies there, two extreme points, right? Your complete fitting a straight line will be different, right? So one or two anomaly points, it is very outliers, right? So this algorithm will be very sensitive. And when you have, let us say, v1, v2, v3, I consider these as the corresponding axis, right? The coordinate axis. So that means the I variance axis, let us say x, y, z, right? Whichever v1 is the higher, v2 is the next one, v3. So they are nothing but the high variance and low variances, right? So these are all some of the disadvantages. In fact, when you have the covariance matrix, right, so it is very difficult to find out the eigenvalues and eigenvectors, right? So you can think in terms of time complexity. So given, in fact, you can you might have done with your numerical analysis how to find out the top eigenvalues. So try to reduce, right? As far as I know, we can do order n cube, where n is the n cross n is the matrix, right? So these are all some of the disadvantages as well in PCA, right? So anyway, I told that we'll talk about the example for PCA, and before that, the next concept we'll see linear discriminant analysis. So LDA. So unlike your PCA, it is similar to PCA. So here what is happening? This is for the supervised learning algorithm. LDA is for the supervised learning algorithm. I'll take some water and I'll start this again. Right? We'll have a little break, 2 minutes.
Yes, sir.
Okay, thank you. So LDA is for the supervised learning algorithm, right? It's again, we are going to have the concept of eigenvalues and eigenvectors, right? So here, exactly like a clustering problem, so between the classes, you have to maximize. For example, you have a plus class and minus class, right? So the distance should be as maximum as possible, right? So that is what the main idea. So maximization problem, right? Between the classes. So you're going to have between class matrix. All right. So here, what we are going to do, we are going to find out again the eigenvalues and eigenvectors. All right. So one eigenvector will tell you how maximize, right? It will be, the classes will be separable. All right. One eigenvector. So assume that I am I'm considering a 2 by 2 matrix. Right. So that means I will have two eigenvalues and the corresponding eigenvectors, right? Two eigenvectors. The maximum eigenvalues corresponding eigenvector, so will maximize the separation between the classes, right? So that we are going to see over here. Right. So let us consider you have set of data points, you have blue and green data points. Assume that mu1 and mu2 are the corresponding means, right? S1 square and S2 square are the corresponding variances, right? So let us assume here you have. So what exactly we are going to do, the objective is you have to maximize the distance between the means. The mu1 and mu2 should be maximized and the variance should be as minimum as possible, right? So this is what exactly we are going to deal, right? So here I talked about the mean. Mean is as maximum as possible, and the standard deviation should variance should be minimum, right? So based on that, the equation that you are seeing is the Fisher's equation, right? So argument of maximization of JW, right? So you are going to find out the vector. You have set of points. You're going to find out the vector, whereas when you are going to project this, you will get the separation between the classes, right? For that, I have to do the maximization of J of W. That means your numerator you have mean mu1 minus mu2 the whole square, and the denominator you have Sn square plus S2 square, right? In fact, J of W, when I define it, is W transpose SB. SB is nothing but between class matrix, right? Between the class matrix should be maximized, and within the class, suppose I have certain pluses and certain minuses, all right? So they should be plus. Those plus points should be as near as possible. All the plus points. Assume that you have n plus points, 100 plus points. All 100 plus points should be in the cluster as minimum as possible, right? And your minus, those should also be as minimum as possible. But whereas between plus and minus, it should be as maximum as possible. So that's why SB goes in the numerator, maximization, and SW in the minimization. And if you look at the first equation, argument of maximum, right? So obviously when the denominator is minimization and it is in the denominator, it is a maximization. 1 by minimization is nothing but the maximization. So mainly this is the maximization problem, all right? So in fact we will take an example, and in fact binary class problem, and we'll see how we are going to calculate this SB and SW, right? So once I have, you can see I can make it out as a eigenvalue and eigenvector problem, right? So assume that I have SW inverse into SB. You will get an idea from the equation number 2. I consider the matrix SW inverse into SB because W you have to minimize, B you have to maximize. SW inverse into SB, I consider this a A matrix. Now with this A matrix, I am finding out eigenvalue and eigenvector. So small v will be eigenvalue and W will be eigenvector. So once I find this eigenvalue and eigenvector, right? So the main idea, right? We'll come back to eigenvalue and eigenvector. So the main idea is you have to maximize SB and minimize SW, right? Within the class, I said plus all the pluses should be as near as possible. All right. So we are going to calculate within class matrix and between class matrix SB. All right. So between class plus and minus as maximum as possible. Therefore, the separability will be preserved. So how we are going to find out the separability? So that we are going to see. So given data should be standardized, and we are going to compute the within class matrix, and we are going to compute the between class matrix SW and SB. So once you are finding out, you are going to projection. So I am going to choose the largest eigenvalues corresponding eigenvector, and then I am going to drop down. I am going to project, right, all in this eigenvector. This is what exactly we are going to do in linear discriminant analysis, and based on that, I can make the prediction. Right. So now we talked about, right, this SB and SW, right, between class scatter matrix and within class scatter matrix. So how do you find? All right. So let us say, suppose you are having two classes, right? So when you are having two classes, you will find the mu1 and mu2 mean. So once I find the mean, n is the total number of points, or in that particular class, I have ni is the total number of points in that particular class. You call it as a respective class, size of the respective class. And mu I is the mean of that particular class. Mu is the overall mean. Given complete set of data points, what is the mean? That is mu. And mu I is particular class, what is the mean. Right? So based on that, I have a SB matrix. Right? I have a SB matrix. The idea is we have to maximize this SB. Right? So let us assume you have set of data points. The data points are 1, 2, 2, 0, 3, 1, and 0, 2. Right? Find out the mean and variance. And the class label is saying no, 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 no. Right? The class is no. And another class is S class. Right? Binary class. One is 0, another one is 1. You have set a point 6, 8, 5, 7. The mean, individual mean 5.5, 6 plus 5 by 2, 5.5, 8 plus 7 by 2, 7.5, and I am finding out the variance. Right? So it's the individual mean. And now I can find the overall mean also. You have 1, 2, 2, 0, 3, 1, 0, 2, 6, 8, 5, 7. Find out the overall mean. So each one I am estimating, right? Mu1, 1, mu1, 2, mu2, 1, mu2, 2. We have found out, right? 1.5, 1.25, 5.5, 7.5. Similarly, I can calculate the variance, right? 1.25, 0.69, 0.25, and 0.25. So mu1 is nothing but 1.5 and 1.25. Mu2 is 5.5 and 7.5. Almost I have got all the data, right? So now when I calculate, right, in fact, I can calculate based on this formulation. Right. So I have a sample mean is this 1.5 and 1.25. Global mean is nothing but everything 1, 2, 2, 0, 3, 1, 0, 2, 6, 8, 5, 7. So when I find the global mean, which is 2.83 and 2.33, 3.33, and I can calculate mu I minus mu. I'm just going for this formula, mu I minus mu. So once I find this, I can always find the between class scatter matrix, right, which will not be difficult for class 2. One is for class 1, another one is for class 2, and then I will come up with the between class matrix, which is nothing but 21.33, 33.33, 33.33, and 52.08. So it's a 2 by 2 matrix, right? So this is how you calculate between class matrix. Similarly, I have a within class matrix. So within class matrix, which is nothing but S1 plus S2. Right? S1 is nothing but covariance matrix for data 1. S2 is covariance matrix for data 2. So this we have already done in PCA. Similar to that. Okay. So then S1, we know how to calculate. Right? Given set of data points minus mu into given set of data points minus mu I transpose, find out. This we have already done in PCA. Right? So if I add both, S1 is covariance matrix for class 1, S2 is the covariance matrix for class 2. If I add both, I will get within class matrix. You call it as SW. So now you have the same set of points. I am going to calculate within class matrix x1, x2, and I'm subtracting with the mean 1 and mean 2. I will get this. This is another class. If I subtract with the mean 2, 5.5 and 7.5, I'll get this. Right? Now, if I calculate the covariance matrix, you know that. Right? When you have two dimensions, you will have 2 by 2. x1, x2, here also x1, x2, class 1, x1, x2, class 2, x1, x2. You will get 2 by 2, separate 2 by 2 covariance matrix. You are seeing S1, S2, they are the covariance matrix for class 1 and class 2 respectively. If I add both, you call it as within class matrix, SW, which is not very difficult to calculate. So once you have this, I have to find out. Now you have two matrices, SW and SB. Find out the eigenvalue of SW inverse in the SB, right? I'll again come back with one more example. Why we require SW inverse in SB? We know that because within class matrix you are minimizing and between class you are maximizing. When I take the numerator SW inverse into SB, maximization problem, find out the eigenvalue and the corresponding eigenvector. All right. So once you are, all right, for example, here in this case, one eigenvalue you are getting 3.55 into 10 power minus 15. Another one is 3.53 into 10 power 1. So naturally eigenvalue 2 is the maximum one. So that is the corresponding eigenvector 2, right, which is the maximum for eigenvalue, right? Eigenvalue 3.53 is maximum, right? The corresponding eigenvector is minus zero point 0.5 and minus 0.8. So we are projecting all the data points into eigenvector 2 and then solve the problem further. In fact, that will give you the larger separability, right? In fact, we will consider that particular one case, and then I will project, right, how the separability is going to happen. So now what we are doing, once you are finding out the eigenvector, right? For example, here eigenvector 2 is having maximum variance, right? Larger variance. So in that case, when I project all the points to this eigenvector 2, so it's a usual projection vector. You have set of data points. One eigenvector is there. You call it as a vector. I am projecting all the points into this vector, right? So which is not very difficult, right? Most of you are having a mathematics background. It's a projecting a vector, projecting onto the vector. You call it as projection vector. All right. So what is the major difference between LDA and PCA? So the case of PCA, the components, right? You maximize the variance. PC1, PC2, PC3, PC4, right? We choose PC1 and PC2. If I take PC1 and PC2, I could get the variance, maximum variance. Whereas in the case of LDA, you have to separate out as much as possible. All right. So the separation should be as maximum as possible. That is the difference between LDA and PCA. All right. Also, we can use LDA for the classification algorithm. So now what we do, we try with, let us say, Gaussian curve or Bayesian curve. And then when we plot it, I can find out the separability very well, right? Anyway, I'll give the physical example, and these are all the major difference between PCA and LDA, all right? Anyway, I'll come back to that before concluding with LDA, right? I'll come back to this particular difference. We will take one example. I still have 15 minutes. Right? So let us consider one problem, all right? One application. So let us assume you have a CCTV footage. Let us consider I have 12 different CCTV footage, right? Which is the multidimensional data, right? For example, a video, you have a XY axis, and Z axis you have at a time how many number of images. For example, at time t is equal to 0, I have, all right, 200 images, all right, frames per second, 200 frames. In a second, I have 200 frames. 0th second, you have 200 frames. First second, you have 200 frames. Second, you have 200 frames. Imagine you are given 30 minutes video, which is a very big data, right? You have a XY image, and then In the time domain, you have number of bands, number of frames, right? So let us have the CCTV footage, 12 different CCTV footage. The problem is to find out in a parking lot, is there any activity going on or any action going on, right? For example, two people are walking in the first video, and the second video, a person is walking with a shadow, and the third video, three people are walking. So now, how do I get the dynamic object, right? How do I get the dynamic object? So, for example, here in this video, let us take a first video. You have several static objects. Car, two cars are there, I believe, or in the second video, you have 4 or 5 cars, all are static. Whereas a person is moving. So when I have to find out the moving object, you are extracting the dynamic object, right? So for this, you have to use the optical flow algorithms. 2 or 3 of my students have done the separate PhD problem on optical flow, right? Finding out the optical flow. So optical flow is nothing but which will give it's a very good mathematics problem, right? So for example, a simple one, if I consider frame number j and frame number j plus 1. So frame number j, let us say the people are walking. So j plus 1, your coordinates are your pixel values will be different, right? So they might have moved in x direction and y direction. They might have moved, let us say, a fraction. So obviously there is a change in j and j plus 1. It's a simple example. Simply I subtract all the gray level values, I subtract with j plus 1 gray level values. Assume that I'm subtracting with j. You can find the difference. In fact, you can find the difference like this. So slightly advanced. I'm going slightly advanced. Advanced means advanced optical flow algorithms. I can find these white blobs, right? So that means in a given video, I can able to separate out, right? I can able to separate out the dynamic objects. The white portions are nothing but in the last one, right? The white portion. So here, right? The white portions are nothing but the blobs, right? You call it as the binary image. The binary images are nothing but the moving objects. So when if you are able to find out the moving objects in a video, you call it as optical flow, right? Optical flow algorithm. Based on the optical flow algorithms, I can able to find out the moving objects. So once you assume that, once you find out the moving objects, assume that I find skeleton, all right? From assume that thousands of pixels, I am reducing to tens of pixels. So skeleton, all right? Thousands of pixels will be reduced to tens of pixels. That means I'm eliminating few data, right? And selecting, let us say this skeleton only, feature selection. From this selected features, I can able to, from this selection, I can able to extract the features. For example, walking. Walking feature will be different from fighting features or running features or kicking features, right? So I can able to extract the features. So once I extract the features during testing, I apply some, let us say LDA tree, LDA algorithms, LDA tree, or a neural network to find out the action. So this is a traditional machine learning algorithm, right? So given skeleton, I can use the bounding box. Bounding box, let us say I am dividing into n sectors, ellipse. Let us assume the second sector, I am considering all the pixels, right? And divide by the total number of pixels. For example, jth frame, right? F2J stands for second sector. What is the number of pixels? And divided by the total number of pixels. So jth frame, I have a feature Fj. Assume that you have all consecutive frames F1, F2, F3, Fr, right? So F is called as a feature vector. For example, running sequence, I have F. Walking sequence, I have F. Fighting sequence, I have F. So whatever action you are saying, I have the feature vector, All right. So once I have a feature vector, so let us assume, right? Again, I am coming back to the linear discriminant for binary class problem, right? We'll take an example and work it out for LD, right? Binary class, yes or no, pass or fail, right? So assume that I have set of red points and set of blue points. I'm going to classify this, right? You are given x1 and x2. Find out the mean, which is not difficult, mu1 and mu2. And next step, you are finding out the covariance matrix. X minus mu1 into x minus mu1 transpose. I am finding out the covariance for S1, which we have done. Similarly, S2 covariance matrix, right? So once you find S1 and S2 within class scatter matrix, within class scatter matrix is nothing but adding these covariance matrix SW, right? And between class scatter matrix, we are finding mu1 minus mu2 into mu1 minus mu2, the whole transpose. You are getting SB, right? And this will be your SB matrix, between class scatter matrix. So we calculated SW, we calculated SB. Now we calculate SW inverse into SB. The reason is in the Fisher's equation, you are having WSB into W transpose SBW divided by W transpose SW into W. So that means your within class should be as minimum as possible and between class as maximum as possible. So when I want to make it as a maximization problem, I put it in the numerator. So numerator, when I bring, it will be SW inverse. So now I am finding out the eigenvalue and eigenvector for SW inverse into SB. So these are all two eigenvalues. Lambda 1 is 0 and lambda 2 is 12.2007. We already calculated, right? SW and SB. So when you work it out, one eigenvalue is 0, another eigenvalue is 12.2. So now when I find the corresponding eigenvectors, we have W1 and W2. So now I choose the largest eigenvalues corresponding eigenvector. You may ask the question why. You will get an answer soon. Otherwise, this is a direct formulation to calculate the largest eigenvalues corresponding eigenvector. Whatever way, right? This is a simple one. One eigenvalue is 0, corresponding eigenvector is minus 0.5 and 0.8. Another eigenvalue is 12.2, corresponding eigenvector is 0.9 and 0.41. In fact, you get 0.9 and 0.41, the direct approach. All right. So now, physically, we will see. So you have set of data points, red points and blue points. Right. I have the smallest eigenvalues corresponding eigenvector. The pink line is the smallest eigenvalues corresponding eigenvector. So let us rotate this vector into x-axis. Obviously, I am going to rotate all the points to x-axis, about to x-axis, and then project all these points, or project all these points in these eigenvectors, rotate to x-axis. And you can see, right, you have red points and blue points in x-axis, right? So that means your two-dimensional points, you have reduced to one-dimensional points, right? You have projected into one-dimensional point, and then you are trying to separate it out, right? I draw the Gaussian curve for the blue points and for the red points. You can find they are overlapping, right? The reason is we have chosen the smallest eigenvalues corresponding eigenvector. We have not got the good separability. You call it as a bad separability, all right? So is there any chance I get the good separability? Yes. You use the largest eigenvalues corresponding eigenvector, right? So this green in color is perpendicular to the pink in color, right? Now I project all the points into this eigenvector, rotate to x-axis. You can see the red point and blue points are separated out properly, right? This is called good separability. That is why LDA can be useful for the classification as well. All right. So here you have found out this particular eigenvector and project all the points into these eigenvalues. Right? You have projected all these points into these eigenvectors, these eigenvector. Right? You projected all these points into this eigenvector. So that means your two-dimensional problem reduced to single dimension. You call it as a dimensionality reduction, as well as you can find the good separability. Right? Whereas if you choose the smallest eigenvalue, I have the bad separability. All right. So that is why this problem can be used for the classification also. LDA can be useful for the classification also. Right. And in fact, this concept is useful for generative AI. All right. So suppose, assume that I have 10 data points. The 10 data points whose average is 50. I want to generate a 11th point. Which point will you generate? The value should be 50. Assume that I'm asking you to generate 2 points. What do you do? X1 plus X2 should be 100. Right? 10 points average is 50. I want to generate 2 points so that my average should also be 50. So X1 plus X2 should be 100. Any point you can generate which satisfies X1 plus X2 equal to 100. All right. So I am the discriminator. If you say X1 plus X2 equal to 100, you are right. You may ask the question, what about X1 plus X2 equal to 99? You are wrong. Right? Because the average will not be 50. Suppose you are selecting the points, X1 plus X2 is 99, 2 points. You are generating 2 points, where X1 plus X2 equal to 99. Already 10 points are there, average is 50. So now 12 points, can the average be 50? No. Right? So you will have the generator and discriminator. This is called generator and discriminator. This is how exactly in the neural network it is being used. Right? If you study variational autoencoders, right? So you can talk about the generator and discriminator. Right? So for example, in this case, suppose I choose some more red points and I keep my Gaussian intact. Some more blue points, Gaussian intact, and then do the reverse process. Right? Set of more number of red points, more number of blue points. This is how the generative AI is doing. Right? For example, the area like medical imaging, you may not get lot of data. Right? Maybe 400 images. Getting 400 images in a hospital is a big task. Those who are working in medical imaging, you know that. Right? From these 400 images, can I generate 4,000 images or 40,000 images? Yes, it is possible. All right? Based on generative AI. That means I have told the story of keeping the mean intact or keeping the Gaussian intact. You can able to generate, right? Or those who are really interested, you can talk about the auto. You can study about the auto encoders in deep learning, right? So coming back to the problem, I'll just finish it. So maximization of J psi, your SB should be maximized and SW should be minimized. So denominator minimize means it is a maximization problem. And we know SB matrix, we know SW matrix. So now the problem is with one iteration. So assume that I am finding out LDA, one iteration. Can it work? Right? It need not be. For example, I have alpha, beta, gamma, delta class. I apply one iteration. That means I want to separating 4 different classes. I want to separate 4 different classes. So one iteration, you may get, let us say, alpha class, 97% accuracy. Right? I want to further use LDA for that particular 97% accuracy only I'm getting. I have set of alpha, beta, gamma, delta. Right? I may improve. Right? So that means you are going to develop a tree. Numerical analysis point of view, you are not stopping in one iteration. You are doing further iteration. So the computer science point of view, you are generating a tree. You call it as LDA tree. So the idea is in the leaf node, you might be getting the accuracy more. That means the separate classes in the leaf. That is what the idea of LDA tree. All right. So if I use a single shot, that means only LDA algorithm, I may end up with 95.8% accuracy. whereas LDA tree based is giving 98.5% accuracy, right? So this is what the difference between LDA and PCA. PCA is for the unsupervised learning and LDA is for the supervised learning. So the main idea is PCA is maximizing the variance. Whether here you are having maximizing the between class matrix, right? So here I am getting, let us say, the important components. So those components are best representation. So here it is best discrimination, right? So we had a lambda 1 and lambda 2. With the help of one lambda 1, when we are finding out the eigenvector, separability is not good. Whereas another one, separability is good. So the best discrimination. So we choose lambda 2 and the corresponding eigenvector. All right. So it identifies, the PCA identifies the direction of the maximum variation, of course. And here in this case, the between class matrix and within class matrix, the ratio should be maximized. That means SW inverse into SB should be maximized. So this is a major difference between PCA and LDA. All right. So anyway, these questions I'll give as an assignment. You can think about that. And in this lecture, we talked about the principal component analysis and LDA. In fact, for the case of LDA, we had seen the example, right? I dealt with image processing example. And in the next class, I have to talk about the mathematics of image processing. So there I will take one example for principal component analysis. All right. So in the meantime, we introduced our first book. In fact, recently we got our second book also. Right. I talked about the basic machine learning. So those who are interested and you are well versed with machine learning, you can start reading or you start getting this book first. And we have a book called Deep Learning Through the Prism of Tensors, so completely a mathematical approach.
Thank you, sir.
One second, I'll just complete with the acknowledgements.
Yes, sir.
So these are all the funding agencies. So we are doing a project for ISRO, DRDO, SCRB, MATI, and IIT are sponsored few right apparatus, and we have done a work for Samsung also. And I thank MV and Machine Vision and Machine Intelligence Lab at IIT Roorkee, all my students. Thanks to Department of CS, and you have my lab website. You can go through, right? So there are several areas. Maybe one more time we are meeting. All right. So before that, what you can do, you go through what are all the other work is being done. All right. And this is my website. And if you have any query, you can also contact through this email ID. And if you have any questions, please, over to you, Dr. Priyanka.
Thank you, sir. So any questions, participants, you can post